So until now, we've only looked at projectiles that were launched horizontally. They had no vertical velocity until they left whatever ledge they fell off of. We saw that we could analyze such motion using the idea that horizontal and vertical are independent. I called that the Vegas rule. What happens in X stays in X. What happens in Y stays in Y. And furthermore, we see a constant velocity position time graph in the X dimension because gravity, a vertical force, doesn't affect it. We see a parabolic position time graph in the Y dimension because we have the constant force of gravity affecting it. So the point of this video is going to be to generalize these ideas and deal with non-horizontal launches. So we're going to, after this video, hopefully be able to deal with motions where objects are launched at a downward angle. Notice the similar position time graphs. Or at an upward angle. So I want to start by kind of looking again at our horizontal launch angles. Then we'll look at a upward angle launch, and we'll talk about overall strategy. So here's the motion we studied previously. This small orange doll falling off the tabletop with a horizontal velocity. And then once it leaves, it starts to acquire a vertical velocity and hits the ground. We started to understand that by looking at its initial horizontal motion kind of staying the same. Notice that I have a velocity arrow that's drawn the same length in each of these pictures. But that once it clears the tabletop, a vertical motion starts to grow in. And that vertical velocity gets bigger and bigger. The reason horizontal doesn't change is we have no horizontal forces. The reason vertical does is that we have a vertical force. And the acceleration it causes is what's growing this vertical velocity. So here's tracker's output for this motion. Up top I have my horizontal graph, and it being linear, that shows a constant velocity. Down at the bottom I have my vertical graph, and it being a parabola shows a constant acceleration. And as we step through it, we see on the horizontal graph covering the same amount of distance in each time step. In the vertical graph, we see covering more and more distance. So what I'd like to do is I'd like to look at another motion. In this problem, the doll left the table flat. Our vertical initial velocity was 0, which we could see by looking at these the slope of the graph here, and we could see that it's 0. What would happen if we had a non-zero launch angle? In other words, something got thrown up in the air at an angle. So that would be a motion like this. It does not leave my hands horizontally. It leaves both horizontally and vertically. And then it continues to fly through the air under gravity's influence alone. Let's put that into tracker and see what that looks like. I want you to make some predictions, and I want you to consider what forces are on the ball after I let go of it. So this trajectory seems more complicated at first. We're definitely moving both right and up. But if we look at the graphs, we should see some familiarity here. The horizontal motion is still one of constant velocity. And that's because the same forces are acting as in the doll problem, only gravity down. And the vertical motion is also the same. It's also parabolic. What's different about this graph from the motion of the doll? The slope of the vertical position time graph for the doll at time 0 is 0. That's showing our 0 initial velocity. For the basketball, we have a vertical initial velocity. Our slope is not 0. But the key thing to see here is these are both parabolas. The motion isn't any different. We're just looking at different parts of the parabola. So at the end of the day, the two problems are going to be solved identically. Just like we did for the doll, one horizontal equation, one vertical equation, one equation describing this graph, one equation describing that graph. We're going to do that here. So the thing that's tricky is if we're going to keep horizontal and vertical motion separate, how do we deal with an initial velocity that's at an angle, like we saw with the basketball? Well, if we describe this as both being up and to the right, we could separate its upness from its rightness. So I've drawn this purple arrow going as far to the right as the blue arrow. We're going to call that VOX, the X part of VO. I've drawn this orange arrow having all the upness. It starts at the same height and gets to the same height. We're going to call that VOY. And I think you can see that what I've made here is a right triangle. So if our original vector, our velocity vector, ends up being the hypotenuse, all we need to do to find the right part of this motion and the up part of this motion is right triangle trigonometry. So we're going to take a little time and review how to do that. We're basically going to find the size of these sides. And then VOX, this purple arrow, that becomes our initial horizontal velocity. VOY, this orange arrow, becomes our initial vertical velocity. So we can start solving problems just like we have up till now, but we'll just have both a VOX and a VOY.